Hello, my name is Esther, and I'll be going over constant velocity for Lab 1 of Physics 1. So these are a couple of the things that we'll be going over today, and it will be mentioned throughout each slide. So the purpose of this lab is to be able to observe the motion of an object moving at a constant speed in a straight line. The tennis ball, which is the experimental lab, will be compared to using the Glowscript from the code that we create. And some of the conditions that we'll be going over is that it's rolled on a flat surface. We will not include friction or air resistance. And this will be 1D, so it only applies on the x-axis, and normal force is considered equal to gravitational force for this lab. So the fundamental principles that we have to go over today is Newton's first and second law, where the first law states that an object at rest will remain at rest unless an external force is acted upon. The second law is basically stating that the force is equal to the change in momentum over change in time, which is defined as the mass of an object times its velocity. It's also used to be able to understand how systems and surrounding really interact, which we will go over later on. The two formulas that we are mentioning today are the position update formula and the velocity update formula, which we will also go over later as well. So the setup of this experiment for the experimental is the tennis ball rolling across in one direction across the floor. The surroundings, which are friction, gravity, and applied forces, are negligible for this experiment. And we will use the tracker application to be able to observe the tennis ball going across the floor. The Glowscript application is used for the computational trial, and both experimental and computational initial position is going to be approximately 0 meters. The right side picture is a free body diagram where it shows all the different kind of forces exerted on it, but as you can see, it is not showing constant velocity. So in order to account for that, we're going to set F net, which is your net force, equal to 0, and we will be using the velocity update formula to be able to find what the final velocity is. And when solving it through, you can see that the final velocity is just going to equal the initial velocity in this case. So some of the observations that we will see when I run this video is that the initial position is going to start at 0, 0, 0, and the ball is moving from left to right, meaning that the data should show a linear graph. As you can see on the right side, you can see the linear graph and see the data points of the time and the position and its relations to each other on the bottom. So when putting this into Excel, you can see that we will have to use the velocity average formula to be able to find our velocity for the Glowscript. The data on the right is actually in centimeters, so the first thing you have to do is convert it to meters and then solve it over time, which is 1.45 meters per second. And so now we will use this in our Glowscript. So some of the things we changed in the Glowscript code is that velocity is equal to 1.45 meters per second, as we found earlier. The time is going to be 0.8 seconds in the while loop because that's how long it took. The final velocity is equal to initial velocity, as we saw for the F net equal to 0. And the position update formula was used in line 60 to be able to update the position every single time during the while loop. And so this is the video when you run the code. As you can see, the graph is linear as it should be, and the velocity is constant with it staying as a line. And on the you can see that there was also time and data that we'll be using to compare. So this is the experimental and the computational graph on one graph. The observation is in blue and the computational is in orange, and there is some human error behind here, as the blue should have accounted for its surroundings such as friction and gravity. However, it did not account for that except for a small little dot that is shown not on top of the orange. But overall, the direction should still be linear and positive. So what if the values of x and y were changing? So changing the x or y would change the graph negative because the ball is rolling towards a positive axis. And if either axis flipped, then the result would just end in a negative slope, and all the data collected would still correspond with the data presented. The number of push and pulls cannot be identified when looking for the zero net force. So the velocity constant cannot be found in the experimental experiment, and due to the external surroundings such as friction and gravity, we still wouldn't be able to find an actual constant velocity. As for the computational net force is equal to 0, which we can account for because the code allows us to do that, which allows us to be able to find for V constant. So that is all I have for today, and thank you for your time.